Carbon and its compounds. Welcome to a world where carbon reigns supreme, a world of organic compounds. Carbon, the sixth element on the periodic table, is more than just a part of the graphite in your pencils or the diamonds on your rings. It's the fundamental building block of life, an element that has the unique ability to form strong, stable, covalent bonds with itself and other elements. This ability is what makes carbon the star of organic compounds. When carbon atoms bond together, they form the backbone of these compounds, creating a vast array of molecules with different structures and properties. From the simple methane gas that fuels our stoves, to the complex DNA strands that define who we are, carbon-based organic compounds are everywhere. These compounds are not just abundant, they are essential. They play a critical role in various fields, from medicine to industry and even in our daily lives. In medicine, for instance, organic compounds are used to create life-saving drugs. In industry, they form the basis of plastics, paints, and so much more. And every day we consume organic compounds when we eat, breathe, and even when we use soap to wash our hands. But why are these compounds so vital? Well, they are the key players in many biological processes. They provide the energy we need to live, form the structure of our cells, and even transmit our genetic information. Without organic compounds, life as we know it would not exist. So let's dive deeper into this world of carbon-based compounds. Let's explore how they are classified, how their functional groups are identified, and how they contribute to the making of ethanol, ethanoic acids, soap, and detergents. By the end of this video, you will understand why organic compounds, particularly those of carbon, are so essential to life as we know it. Now, imagine a world with millions of compounds. How do we organize this massive number? Let's start our journey into the world of organic compounds, which are primarily made up of carbon atoms. But with countless organic compounds existing, how do we keep them all straight? That's where the International Union of Pure and Applied Chemistry, or IUPAC, steps in. IUPAC has set a universal system of rules for naming these compounds. So what are these IUPAC rules? At their core, they're about identifying the longest carbon chain in a compound, which we call the parent chain. This chain's length determines the base name of the compound. For instance, a chain of one carbon atom gives us meth, 2 gives eth, 3 prop, and so on. But organic compounds aren't just about carbon chains. They also contain functional groups. These are specific groups of atoms within molecules that determine their characteristic chemical reactions. You can think of functional groups as the personality traits of the compounds. Different functional groups give us different classes of organic compounds. For example, alcohols have a hydroxyl group, while aldehydes and ketones contain a carbonyl group. Each functional group has its own unique IUPAC naming rules. For instance, if an alcohol is present, the suffix -ol is added to the base name. The beauty of the IUPAC system is its universality. Whether you're in New York or New Delhi, chemists can communicate clearly about the structure and composition of any organic compound. It's a bit like the language of chemistry, a language that transcends borders and cultures. So next time you come across a long, complex name like 2,2,4-trimethylpentane, don't fret. It's just IUPAC's way of telling you about the compound's structure. Break it down, identify the parent chain and functional groups, and you're on your way to understanding its chemical nature. With IUPAC rules, we can name any organic compound, no matter how complex. Do you ever wonder what gives organic compounds their unique properties? Well, it's all thanks to something called functional groups. Picture organic compounds like a blank canvas, with carbon and hydrogen providing the base. Functional groups are like the paint, adding color and character, making each compound distinct and unique. Functional groups are specific groupings of atoms within molecules that have their own characteristic properties, regardless of the other atoms present in that molecule. These groups play a pivotal role in determining the chemical behavior of organic compounds. For instance, let's think about alcohols. They have a functional group called the hydroxyl group, which is an oxygen atom bonded to a hydrogen atom. This hydroxyl group is what makes alcohols, well, alcohols. It's why ethanol behaves differently from ethane, even though both are made up of carbon and hydrogen atoms. Another common functional group is the carboxyl group. This group consists of a carbon atom double bonded to an oxygen atom and also bonded to a hydroxyl group. This group is what gives carboxylic acids their acidic properties. It's why ethanoic acid, also known as acetic acid, tastes sour and reacts with bases. And let's not forget about the amino group. This group, made up of a nitrogen atom bonded to two hydrogen atoms, is a key player in the world of proteins and amino acids. So, you see, functional groups are kind of like the secret identity of organic compounds. They are the special features, the signatures that give each compound its unique properties and behaviors. They're what make organic chemistry so fascinating, so diverse, and so incredibly complex. So next time you come across an organic compound, don't just look at the carbon and hydrogen. Look for the functional groups. They'll tell you a lot about what that compound is and what it can do. Remember, functional groups are like the fingerprints of organic compounds. Ever heard of ethanol and ethanoic acids? They're more common than you think. Let's begin by exploring ethanol, a simple alcohol with the formula C2H5OH. It's a clear, colorless liquid that's created through the process of fermentation. In this process, yeast breaks down sugar into ethanol and carbon dioxide. It's quite fascinating, isn't it? This process is the core principle behind the production of alcoholic beverages like wine and beer. But the uses of ethanol extend beyond the realm of beverages. It's used as a solvent in many industries, and also as a fuel source. You might have heard of cars that run on biofuel? Well, that's ethanol for you, playing its part in reducing our reliance on fossil fuels. Now let's shift gears and talk about ethanoic acid, also known as acetic acid. Its formula is CH3-Coke. This is the stuff that gives vinegar its distinctive sour taste and pungent smell. It's manufactured industrially by oxidizing ethanol. Yes, the same ethanol we just talked about. But ethanoic acid isn't just for making your salad dressing tangy. It's used in a wide variety of applications. In the textile industry, it's used in the production of dyes and fabrics. In the food industry, it acts as a preservative. It's even used in the production of plastics and pharmaceuticals. So you see, ethanol and ethanoic acids are more than just chemicals. They're vital components in many of the products and processes we encounter every day. They're in the clothes we wear, the food we eat, the cars we drive, and even in the medicines that keep us healthy. From vinegar to alcoholic beverages, ethanol and ethanoic acids are part of our daily lives. It's a testament to the incredible versatility of carbon and its compounds, showing us that the world of chemistry is not just about equations and reactions, but is intrinsically linked to our everyday existence. Cleanliness is next to godliness. But do you know what makes your clothes clean? Enter the world of soap and detergents, where cleanliness meets chemistry. These essential household items are not just miracle workers in getting rid of stubborn stains. They are actually fascinating compounds with intriguing properties. Firstly, let's unwrap the science behind soap. Soap is a sodium or potassium salt derived from fatty acids. The process of making soap is called saponification, which involves the reaction of a fat or oil with an alkali, like sodium hydroxide or potassium hydroxide. This reaction results in soap and glycerol. Now, what makes soap a cleaning agent? Each soap molecule has a long hydrocarbon chain, which is hydrophobic, meaning it repels water but attracts oil and grease. The other end of the soap molecule is a carboxylate group, which is hydrophilic, meaning it attracts water. When you apply soap to a greasy surface, the hydrophobic ends of the soap molecules attach to the grease. When water is added, the hydrophilic ends of the soap molecules are drawn to the water, pulling the grease with them and washing it away. Let's move on to the detergent. Detergents are similar to soap but differ in their chemical structure and the way they are made. Detergents are also sodium or potassium salts, but they are derived from sulfonic acids. They are made by reacting hydrocarbons, derived from petroleum or other sources, with concentrated sulfuric acid, followed by neutralization with an alkali. The cleaning action of detergents is similar to that of soap. They also have a hydrophilic end and a hydrophobic end. However, detergents have a significant advantage over soap. They can work in hard water. Hard water contains magnesium or calcium ions, which react with soap to form insoluble compounds, reducing its effectiveness. Detergents, on the other hand, do not form such compounds and can clean effectively even in hard water. So the next time you load your washing machine or scrub your hands with soap, remember the fascinating chemistry at play. The world of soap and detergents is more than just bubbles and foam. It's a world where hydrocarbons, fats, and alkalis come together to keep our world clean. Soaps and detergents are not just cleaning agents, but fascinating compounds with intriguing properties. Soap or detergent, that is the question. Now that we've delved into the worlds of soap and detergent, it's time to pit them against each other in a comparative analysis. To start, let's look at their composition. Soap, a product of nature, is made by combining fats or oils with an alkali such as lye. Detergents, on the other hand, are synthetic, derived from petrochemicals, and consist of surfactants, foaming agents, and alcohol. Moving on to properties, soaps are biodegradable and therefore more environmentally friendly. However, they're less effective in hard water because they react with minerals to form a scum that's not easy to rinse away. Detergents, though, perform well in both hard and soft water and don't leave behind any residue. But they're not always biodegradable, which can lead to environmental issues. Now, let's discuss uses. Soaps are typically used for personal hygiene like bathing and hand washing because they're gentle on the skin. Detergents, with their robust cleaning power, are commonly used for laundry and dishwashing, as they can tackle grease and tough stains more effectively. But, like all things in life, each has its pros and cons. Soaps, while they're natural and gentle, can leave a residue and are less effective in hard water. Detergents, while powerful cleaners, can be harsh on the skin and may contribute to pollution if not properly treated. In conclusion, the choice between soap and detergent depends on a number of factors: the type of water you have, the cleaning task at hand, and your personal preference for natural or synthetic products. Both soap and detergent have their place in our lives, each with unique strengths that make them suitable for different tasks. So, the next time you wash your hands or clothes, think about whether you're using soap or detergent and why. So, there you have it, a journey through the world of carbon and its compounds. We've ventured into the realm of organic chemistry, where carbon plays a starring role. It's been quite an adventure, hasn't it? We started by recognizing the fundamental significance of organic compounds. Carbon, the lead actor in this narrative, forms the backbone of life as we know it. It's the building block of all organic compounds, which are essential to our everyday existence. From the food we eat to the air we breathe, from the clothes we wear to the fuel that powers our vehicles, carbon is there, quietly yet indispensably making life possible. Then, we dove into the classification of organic compounds, understanding how they are named based on the International Union of Pure and Applied Chemistry, or IUPAC rules. We discovered that organic compounds are not just a chaotic mix of carbon and hydrogen atoms, but rather, they follow certain rules and patterns that lend them a systematic structure. Our exploration took us to the functional groups of organic compounds, those special teams of atoms that determine how these compounds behave. We learned that these functional groups are like the personality traits of compounds, influencing their properties and reactions. We also delved into the specifics of ethanol and ethanoic acids, understanding their preparation, properties, and uses. We saw how these compounds are not just chemical names in a textbook, but substances that have practical applications in our daily lives. And finally, we delved into the world of soap and detergents, understanding their composition, preparation, and cleansing action. We compared soap and detergents, appreciating their similarities, as well as the key differences that make them suitable for different applications. Remember, organic compounds are everywhere, and understanding them can give you a new perspective on the world around you. So next time you wash your hands, fuel your car, or simply breathe, remember the role of carbon and its compounds in making these ordinary actions possible. It's a fascinating world out there, made even more intriguing by the wonders of carbon.